Very much for the introduction, and also thank you for the invitation for giving a talk in this online seminar series. So first of all, I want to apologize because here it's pretty early morning, so I may be slow, in particular at the beginning of this talk, but I just had a coffee, so probably I just need a few seconds for my brain to start working. So okay, so I can start giving just a few ideas on this work before I start talking about this. So basically, at the end of my PhD, I start getting interested in games. And so I had a discussion with Fabio Fagnani, that was my PhD advisor, and Giacomo Como, and we start thinking about this kind of imitation dynamics that are, as we will see, dynamics learning protocols that are based on minimal information. And we start working on this again at the end of my PhD. Then we had some preliminary ideas and results, but this project was kind of put on hold until last November, when I came back to Turin. Well, I did my PhD for a workshop, and then me, Fabio, and Giacomo discussed about this project that was put on hold. We had some new ideas, and we ended up basically with this project. So, as we said, we'll discuss on imitation dynamics in population games on network with community patterns. So, this work basically deals with learning protocols in games within the framework of evolutionary game theory, which is quite an important and, at least from my point of view, interesting topic, because it allows to model and study how individuals make decisions in social groups. And there is quite a huge literature on evolutionary game theory. And here I just show some of the books that I studied during my PhD when I wanted to start working on this topic. What I found is that most of the literature on evolutionary game theory dealt with best response dynamics. So in best response dynamics, basically, we have the assumption that players have a lot of information on the game they are playing. Basically, we assume that this player knows all the actions they can choose and the corresponding rewards. And these agents update their action in order to maximize their current reward. For instance, imagine that you want to change your mobile phone provider. What you can do is to just go online, look at the performances of all the mobile phone providers you can choose, and decide for the one that maximizes the performance you are interested in. For instance, here, if you were in the US in January 2020, you want to maximize your download experience, you should have chosen AT&T. Okay. And then, of course, this performance can change depending on your action and on the action of the others, and so you can revise it as the time evolves. And in the literature, there are many results establishing convergence to Nash equilibria for this kind of dynamics in the presence of noise, disturbances on networks, and so on and so forth. However, best response dynamics are not always realistic to model how individuals make decisions. This is because in many scenarios, players have limited information on what are all the possible choices they can make. So maybe we can know just a subset of the actions we can play. Or even we may have access to all the information, but this information can be hard to be processed because of big data or just because it's hard to process information maybe we're not familiar with. For this reason, in our daily life, we often base our decision on imitation. And the reason for the success of imitation is that imitation typically relies on minimal information. So in order to imitate, we don't need to know what are all the possible actions we can choose and their corresponding reward, but we just need to have the possibility to interact with other people and compare our action and reward with the action and reward of the others. And through this comparison, we get aware of what are the other actions and their current reward, and we can possibly choose to update our action imitating the one of the others. So in general, the presence of this information that is gathered through a communication network poses some technical issues to the analysis of imitation dynamics. And that's why there are much less theoretical results on imitation dynamics than on best response dynamics. In particular, the results on imitation dynamics mostly present local stability results or the analysis of specific types of imitation dynamics. And most of these results, in particular the most general results, are studied in fully mixed scenarios. However, assuming fully mixed scenarios for imitation dynamics, it's quite a simplistic assumption, because we know from the social psychology literature, both from theoretical studies and from many experimental studies, that people tend to establish more interaction within their social group. And also, we tend to be more influenced by people of our social group of the same age or same gender. For this reason, it makes sense to study imitation dynamics in a scenario in which the population is somehow split in communities and people have a different way of interacting within their communities and between different communities. Okay, so in this talk, we start by formally introducing deterministic imitation dynamics, taking into account this community structure we have presented before, for a class of games that are population games. And I will illustrate them through some examples to show that actually this class of imitation dynamics is quite a large class that encompasses many well-known dynamics, for instance, the replicator equation. Then we will characterize the equilibrium points of these imitation dynamics, and in general, we see that they depend on the game and on the imitation mechanism. And finally, we'll perform an asymptotic analysis for a specific class of population games that are potential games, and under some further assumption on the community network. And we will see that imitation dynamics, under this assumption, converge to Nash equilibria. Okay, we can start with the model. So in this talk, we'll focus on population games. So in population game, we consider a population as a continuum of players with unit mass. The players in this population have to choose between a finite set of actions. And so we can define a vector y called population state, such as the ith entry of this vector is the empirical frequency of I players in the population. So clearly, this vector y, the population state, lives in the cardinality of a-dimensional simplex. So for population games, we assume that the reward for players that are playing action I is the same for all these players and depends on the population state. So even though this may seem a restrictive assumption, actually there are many real-world problems that can be modeled as population games. For instance, one problem can be found in a traffic problem that we will consider as an example in this talk. So imagine that we have a transportation network with an origin and a destination, and the players are drivers that have to go from the origin to the destination. So these drivers can choose between a finite set of paths And the population state is nothing but the empirical frequency of drivers on each one of the paths. So it makes sense to assume that the reward for choosing a specific path is equal to minus the delay on that path. And the delay on the path typically depends on how many drivers are on that path. So in this case, it even depends only on the height component of the population state, but in a more general scenario, imagine that you have maybe intersection between different paths, it may depend on the entire population state. But in any case, it fits this framework of population gains. Okay, so as we said, we are interested in studying imitation dynamics in a scenario in which the communication between agents is driven by a community structure. So we represent this community structure using a network, a weighted network, whose nodes are the set of communities. And we introduce a vector eta that tells what is the fraction of population in each of the communities. And then, as we said, the network is weighted, and so we have a weight matrix W, such that the entry WHK measures the interactions between individuals in community H and individuals in community K. So, given this notion and given the social psychology, the evidence in the social psychology that we said that people tend to be more influenced by their own community, it makes sense to assume that this community structure has self-loops. So then we will use standard graph theoretic concepts to refer to this community network, which means that when the matrix W is irreducible, we will say that the network is strongly connected. And when the matrix W is symmetric, we will say that the community network is undirected. Okay, so given this community structure, it is clear that the population state Y cannot describe how the different actions are distributed in the communities. So we need another variable that is the state variable of the system. For this reason, we introduce a system state variable X that is a matrix of dimension number of communities times number of actions, such as the entry XIH of this matrix is nothing but the fraction of population that is playing I and belongs to community H. So notice that if we sum the rows of this matrix X, we obtain nothing but the population state, while if we sum the columns of this system state, we obtain the vector eta. So when talking about the system state, that is, as we said, the state variable of the system, we refer to the support of the system state as the set of actions that are played by this part of the population in that system state. And we will also say that a system state is balanced if the proportion of I players is uniform in the communities. For instance, here we can see two plots of system states. We see, for instance, an example of a balanced system state where the clearly the fraction of players in the first community and the second community are different because the second community is smaller than the first, but the distribution of players in the different actions, among the different actions, is proportional. While in the second scenario here, we show an example of a non-balanced system state. Okay, so we have almost all the ingredients. And at this point, we can show that the frequency of interactions between I players in community H and J players in community K can be written using the system state and the matrix W, simply as the product of the corresponding entries of the system state that tells how many I players there are in H and how many J players there are in K, times the entry of the weight matrix WHK that tells how many interactions there are between people in H and people in K. Okay. And then when an I player interacts with a J player, we assume that the I player imitates the J player and so switches its choice from I to J with a Lipschitz continuous rate Fij. And these rates Fij define the characteristics of the network imitation dynamics. So now that we have all the ingredients, we can just say that the network imitation dynamics is a deterministic system of ordinary differential equations where we have one equation for each entry of the system state matrix. And in particular, the fraction of I players in community H evolves as according to the difference of two terms. The first term, the summation here, accounts for agents that are playing different actions and belongs to H that meet some people in their community or in other communities that is playing I and imitate it. While the second term is negative and accounts for individuals that belong to community H and are currently adopting action I and interacting with someone that is having a different action, they imitate it. Okay, so before moving to further analyzing the imitation rates Fij that, as we said, characterizes the network imitation dynamics, I want to present a very general result that holds for this deterministic system of ordinary differential equations. That is that the network imitation dynamics admit a unique solution, and the support of this solution always coincides with the support of the initial condition. So existence and uniqueness is kind of a straightforward consequence of Lipschitz continuity of the rates. While what I think it's important to remark is the fact that the support of the solution coincides with the support of the initial condition, which means that if an action is played in the initial condition, it will always be played in the solution of the network imitation dynamics. While if an action is not played in the initial condition, it will never be played. And this is very important because based on this, we can assume without any loss in generality that the support of the initial condition is the entire action set. This because since if an action is not played at time 0, it will never be played. It means that we can, if an action is not played, we can simply remove this action from the set of actions and consider a restricted games with only the actions played at time 0. Okay, so as we said, we can now go into details of the imitation rates. So, what are typical choices, possible choices for the imitation rates? So, one standard choice is to assume that the imitation rate from I to J is proportional to the positive part of the difference between the payoff for playing J and the payoff for playing I. In this way, we obtain the so-called pairwise proportional imitation rule, which is quite well known, in particular in the case of a single community, because this choice of imitation rate is the replicator equation, which is over well known in system biology. Another possible choice for the imitation rate is to use a logistic rule, a logistic formula for the rates, which is used a lot in learning and in diffusion of innovation, in particular in economic sciences. So these are just two possible choices of the imitation rate to show what are typical choices and also to show that actually imitation dynamics are a broad class of learning protocols that encompasses many well-known dynamics. So from looking at these two rates and also thinking about our daily experience, it is quite reasonable to assume that if an action J gives a higher reward than an action I, then it is easier for a J player to convince an I player to change action than vice versa. So we can formalize this intuition in the following assumption. So from this moment on, we will assume that the sign of the difference between the rates from I to J and J to I is equal to the sign of the difference between the payoff. So what I want to comment on this assumption is that this assumption is, as we said, quite intuitive and not very restrictive. And this, for instance, compared to other assumptions that I found in the literature when studying imitation dynamics that are much more restrictive. For instance, when I was studying imitation dynamics, and this was basically one of the starting points of my work, I found this assumption that is typically made to find theoretical results on imitation dynamics, that is basically a kind of the existence of an ordering between the actions. And this, to me, sounds not really intuitive because basically it's saying that if an action J gives a higher reward than I, then there is something that holds for another action L. That is, so to me, this is kind of requiring too much information that typically in this imitation dynamics that relies on interaction between two players that have two agents, it's hard to be verified. So basically I start working on this when looking at this assumption, which seems to me not very natural, I start thinking it was maybe possible to find a simpler assumption under which it was possible to find some theoretical results for imitation dynamics. And from this, finding this simpler assumption, basically we started working on this project. So just want to stress that the pairwise proportional imitation verifies both the assumptions, while the logistic imitation rule in general verifies only assumption 1, but not the more restrictive assumption typically made in the literature. Okay. We have now introduced the problem and we can start presenting our results. So before presenting the results, we need some further notation. In particular, we need to define what are the Nash of the game. So the Nash of the game are configurations in which no player has any incentive to change action, which means basically that everyone is happy with its choice because it is the choice of action that maximizes the current reward. So basically, all the actions that are played give the maximum reward in the current configuration. Then we can define a broader set of configurations that is the set of restricted Nash. In restricted Nash, people have no incentive to change actions between the actions that are currently played, which means that there can be some action that gives a higher reward, but is not played by anyone. So let's see this with a very simple example. So we consider our traffic problem and we consider a simple example with 3 paths, 1, 2, 3, and with a delay that is linear in the number of drivers on the path. So in this scenario, it's quite simple to show that there is a unique Nash equilibrium that is the black dot in the interior of the simplex, while there are other 6 restricted Nash equilibria that are the vertices of the simplex and 3 points on the faces of the simplex. And if we look at more details at one of these restricted Nash that is not a Nash, for instance this one, we see that in this restricted Nash only action 1 and 3 are played, and these 2 actions give the same reward. However, there is an action that is action 2 that is not played by anyone, but which is giving a higher reward. Okay, so we have defined Nash equilibria as a population state, but we can, in the same way, define Nash equilibria as a system state X corresponding to population states that are Nash equilibria. And we do this because we have previously defined the notion of balance system state, and so we can define balance Nash equilibria and balance restricted Nash. Okay, we have introduced the notation we need to study the equilibria of these dynamics, and so we can move to our results. So, first of all, we are interested in finding what are the equilibria of the dynamics. So, in the case of fully mixed scenario, it's not so difficult to prove, and we did it in a preliminary result, that the set of equilibria coincide with the set of restricted Nash. However, the presence of a community structure makes everything a bit more tricky. But what we can find is that if the graph G is strongly connected, then all balanced restricted Nash are equilibria of the network imitation dynamics. And the equilibria of the network imitation dynamics are a subset of the restricted Nash. Basically, this dark green region of balanced restricted Nash are all equilibria, while this light region may be equilibria or not. And in the gray region, we cannot have equilibria. Moreover, if some properties on the arrays holds, we can have a more detailed result. In particular, if the arrays are always strictly positive, like in the case of logistic imitation, then we can prove that the set of equilibria actually coincide with the set of balanced restricted Nash. While if the arrays are zero, whenever if the transition rate from the imitation rate from I to j is equal to 0 whenever I and j gives the same reward, like in the pairwise proportional imitation, yielding the replicator equation. In this case, we have that the set of equilibria coincide with the entire set of restricted Nash, balanced or not balanced. Okay, basically the proof is not particularly interesting. It's not difficult to prove that balanced restricted Nash are equilibria. It's a bit more tricky to prove that the equilibria needs to be restricted Nash, and this so to prove this we need connectivity. So if the network is not connected, it's not hard to show some counterexample showing that there could be equilibria that actually do not belong to the set of restricted Nash. Okay, so now that we have characterized the equilibria of network imitation dynamics, the question is, does actually the dynamics converge to this equilibria? And in general, the answer is no. And to show this, it's just enough to simulate a very well-known game like rock, paper, scissors and simulate imitation dynamics for this game. We plot the results and we see a very nice oscillating behavior, which means that in general, it's not true that the network imitation dynamics converge to Nash equilibria. We need some further assumptions. And we need some further assumptions both on the game and on the network. Okay, we will start with the assumption on the network. And in particular, from this moment on, we will study what further properties network imitation dynamics have whenever the network is not only connected, but also undirected. So to simplify the notation, we can write the dynamics for the population state. So we say that yi of t is nothing but the sum of over all the communities of the sum of the row, the ith row of the system state. So for network imitation dynamics on connected and undirected community networks, we can prove an important property that is that the set of restricted Nash is positive invariant. And this will be quite important to prove convergence. And what I want to stress is that in general, if the network is not undirected, this is not true. And also here, it's not hard to show counterexamples. The second result is a little bit more technical, and it refers to a local repulsiveness result for restricted Nash equilibria that are not Nash. So basically, we can prove that if the network is connected and undirected, then if system state is a restricted Nash but is not Nash, then we know that this means that everyone in this restricted Nash has the same reward. However, there is some action I that is not played by anyone, which is providing a larger reward. Okay, so our result says that for this action I that provides larger reward, there is a neighborhood of the restricted Nash that is not Nash, for which if yi is greater than 0, then also yi dot is greater than 0. So in plain words, it's saying something like that if locally these restricted Nash that are not Nash are kind of repulsive if coming from a direction of an I that is not played in this Nash, but it's providing a larger reward. And this will be used to prove convergence. However, these results, again, are only local results. So far it seems not enough to prove a global result convergence to the set of Nash. For this reason, so to have a global result, we need some more assumption on the game. And in particular, we need to assume, not need, but it is sufficient to assume that the game is potential. So potential games are an important class of games where there exists a potential function phi such that the differences in the rewards are somehow linked, are equal to the difference of the corresponding partial derivatives of the potential function. So potential, as we said, are quite an important class of games because they include many well-known games like coordination games and congestion games, for instance, the traffic example presented before. And also there are important links between the potential function, in particular the stationary points of the potential function, and the Nash of the game. Okay, and for potential population games, in strongly connected and undirected networks, we can prove that the potential, actually minus the potential, works as a Lyapunov function. In particular, the derivative of the potential along the vector field always verified is always non-negative, with equality verified only in the restricted Nash. Okay, so now if we put together all these results, so the presence of a Lyapunov function, the fact that the restricted Nash are invariant, and the local repulsiveness results, we can prove that if the graph is undirected and connected, and if the game is potential with a finite set of Nash that are in the interior, so notice that we need some further assumption on the Nash, we need them to be finite and in the interior of Y, then the imitation dynamics converge to a Nash. And this can be obtained basically by putting together the three propositions we presented before. So, moreover, if the imitation rates are strictly positive, like the case of logistic imitation, then we can prove not only that the dynamics converge to a Nash, but that the dynamics converge to a balanced Nash. So, basically, observing again the schema shown before, what our result says is that the dynamics converge to this green set, and if the rates are always strictly positive, like in the logistic imitation, we know that it converges to this dark green set. Okay, just a quick remark. As we said, we need some further assumptions on the set of Nash equilibria. This assumption can be relaxed at the cost of having a weaker convergence result. In particular, if the set of Nash is not finite, we cannot actually prove convergence to state that is Nash, but we can just prove that the distance between the trajectory and the set of Nash equilibria goes to 0, while if there are some Nash not in the interior, then we still can prove convergence to a set, but this set is not only the set of Nash, but we have also to include some restricted Nash that lie on the face of the boundary of the simplex on which there are these Nash equilibria that are not in the interior. Okay, so to better present these results, we can go back to our traffic example, which with this linear delay is a potential game, and for which, as we said, there is a unique Nash equilibrium that is in the interior. So all the assumptions on of our theorem are verified if we take a connected, undirected community network. And for instance, we can take a network with 2 communities, and we find that there is a unique balance Nash equilibrium. Okay, so let's see what the network imitation dynamic do in this case. And if we choose a pairwise proportional imitation that, as we said, do verify the theorem, but not the corollary, we see from the first figure that actually the population states converge to the unique Nash equilibrium as predicted, but the system state converge again to a state that corresponds to a Nash equilibrium, but is not balanced. Instead, if we consider the logistic imitation rule that actually verifies also the corollary, we see that not only convergence of the population state to the Nash equilibrium, but also convergence of the system state to a balanced configuration. Okay, so to wrap up, we have proposed and studied imitation dynamics in potential population games on networks, in particular on networks where the community structure determines how individual interacts and how the imitation dynamics, so how individual interacts and basically determines how the imitation dynamics evolve. And we have characterized the set of equilibria for these imitation dynamics. And we have shown that for potential games on connected undirected networks and with some further assumption on the Nash equilibria, we can prove convergence to the set of Nash equilibria. So in our current work, we want to extend these results, in particular to go beyond potential population games, which we show it is a sufficient condition to prove convergence to Nash, but we are pretty sure it's not necessary, so we can relax the assumption of having an exact potential game to prove convergence. And then we want to extend our analysis for asynchronous and stochastic imitation dynamics. Actually, we already have some preliminary results on stochastic imitation dynamics, but only in fully mixed scenarios. So in cases where the communication network is a complete network and want to extend our result to more realistic cases. And then we want to expand our formalism and consider multi-population games and more general scenarios. So I hope you have enjoyed this talk, and if you want to read more, okay, some preliminary results in fully mixed scenarios are published in this paper, in this conference paper, while most of the results presented in this talk actually are in this paper, Network Imitation Dynamics in Potential Games on Community Networks, which has been accepted just a few days ago in the IEEE Transaction Control on Network Systems, and is available now only on a preliminary version on arXiv. So I just want to conclude by thanking all of you for your attention and thanking again Giacomo Com and Fabio Fagnani who worked with me on this project.
Thank you very much, Lorenzo, for the interesting talk. Are there any questions for Lorenzo?
I have that one. Sorry.
Yep.
Thank you for the talk. It was very interesting. Since you were mentioning the rock paper scissors game, did you consider studying limit cycles analysis?
Yeah.
Or convergence analysis?
Yeah. So one of okay, it's not mentioned in the current ongoing direction, but one other thing we are currently thinking of working on, and so one of our future works will be also to study scenarios like rock, paper, scissors or other games, and to study the emergence of limit cycles for the network imitation dynamics. So the answer is yes, it's something actually we are considering and we want to better study. So under which assumption on the network and on the imitation rates, we can observe the emergence of limit cycles.
Thanks.
Any other questions for Lorenzo?
I have one. So in one of the convergence results, you require the finiteness of the Nash equilibria. Is that almost always verified, or is it very unlikely that you will have an infinite set of Nash equilibria?
Well, it depends on the game. So you can, in general, so in many real world scenarios, actually you have, well, of course, it depends on the potential, but if the potential is convex, then there is a unique Nash equilibrium and so on. So in general, if there are, for instance, two actions that provide the very same reward, then any combination of this action can provide the same reward. And so if basically imagine a scenario in which the potential, so I'm thinking, or maybe a potential that does not depend on, I don't know, a certain action, then you can have that the line cubes of the potential are somehow of a higher dimension on the simplex. So there can be, it's not so difficult to find scenarios in which actually the set of Nash is not finite. In many cases, these scenarios can be somehow simplified. So if a potential does not depend on, so in general, it means that if a dynamics does not depend on a specific action, then it makes sense possibly to study the dynamics removing that action and so on. So in general, I would say that it's easy to find examples in which there is not a finite set of Nash. However, most of these examples are not really meaningful from a real world point of view.
Thanks. Thank you.
Okay, thanks again. If there are no more questions for Lorenzo, let's thank him again for his talk at this very early time in Europe. Thanks, Lorenzo.
You're welcome, and thank you again for the invitation.